Hello, everyone. I am still sick, and I have hope to be back on campus soon. Um, so we're going to do a Zoom lecture today, and luckily, I'm not going to do it live because I don't feel well. And you can just watch this on your own time. But today we're going to finish up talking about measurements. A couple weeks ago, we talked about common measurement techniques and different units of measure that we could use. And today we're going to talk about a specific instrument called a clinometer. And I'm sorry if you can hear the dog in the background. She's being very annoying right now. But today we're going to talk about specific measurement device called a clinometer. And on Friday, if I'm feeling well, we will actually get to use the clinometers, which will be really cool. So we're going to wrap that up, and I am going to share sound because we're going to have the video later. So our agenda for today is talking about geodesic versus planar measurements. I know we had a question about that during our lab last week. Then we're going to talk about this device called a clinometer. We're going to talk about percent slope, slope distances, horizontal distances, and then we're going to get into an introduction to pacing, and we'll actually do pacing on Friday. So planar measurement. So we had the question last week in lab that was, it was either last week or the week before, I don't remember. But how do geodesic distances differ from planar distances? And so I wanted to re-emphasize those differences today. So first, what is a planar? So a planar is any flat surface that exists, right? So then planar measurements are measurements that occur on that flat surface, like you can see here in this Mercator projection map, right? So a planar measurement is a measurement on this flat surface projection of a map. So when we use geographic coordinates, planar measurements cut through the curved surface of the Earth, right? So we have the Earth is curved. We have that projection onto a 2D surfaces. And so with that measurement, we're cutting through that 3D-ness of Earth and making a straight line, a shortest distance between 2 points. So the measurements tend to be shorter than an actual true distance on Earth. Um, and we see that measurement error becomes greater as the length of the line increases, right? So that if we were measuring between like Brevard and Charlotte on this map, right? That distance would have a smaller error than if we were measuring between Brevard and Los Angeles, California, right? Because Brevard and Charlotte are a lot closer together. And so the curvature of the Earth doesn't affect it as much as the curvature from Brevard to Los Angeles, right? So this brings up an important point that it's good to know which projection you're using for you to make measurements, planar measurements on that projection, because depending on where or which projection you're using, the Earth's surface might be distorted, right? And so that brings us back to the fact that we cannot make a perfect 2D planar measure, a planar map, right? We cannot make a perfect 2D map. So if we are going to use a 2D map, this planar map to do measurements, we definitely need to pick the most right projection for our area. So again, if we were doing a projection, a measurement, excuse me, from Brevard to Charlotte, we might want to use a projection that is within the state plane projection because that one is developed specifically for North Carolina. However, if we were using that measurement from Brevard to Los Angeles, we would want to use a different projection that better keeps the true distances from North Carolina, from East Coast to West Coast, right? So it's good to know which projection you're using to determine how accurate your planar measurements are. So again, just to reemphasize, planar measurements are these flat surface 2D measurements that cut through the curvature of the Earth, right? They're a flat surface. They cut through that curvature. It no longer exists. So that brings us to the geodesic measurements. And so the first question for me is, what does geodesic even mean, right? So we have to think about what does geodesic mean. And it's defined as the shortest distance that exists between 2 points. So you can see on both of these figures, we have 2 points. And geodesic is just the shortest distance between those two. So then when we talk about geodesic measurements, we're talking about measuring the geographical distance that then uses the curvature, so that non-planar surface of the Earth, right? And so planar measurements, 2D surface, straight line between the two, no curvature. Geodesic measurements are distances that take into the curvature of the Earth, right? And so as we talked about before, when we were talking about datums, there are a lot of different Earth models that are out there, and there's a lot of different models, and therefore the center of those models is all different, right? And so with all of those models that are out there, the two most common that are used are the Great Circle model of Earth, which is this one that you see here on the bottom of the screen. And it's just the Great Circle. We have a great circle, we live on a great circle, right? And then the second most common is this geodesic line. So this is still a planar map, and you can see that planar measurement here in the blue line. But the geodesic measurement is this red line. That's the actual measurement taking into the curvature of the Earth, taking the curvature of the Earth into those measurements overall, right? So this geodesic measurement contrasts to those planar measurements, which again cut through the Earth's surface to provide measurements. Here, instead of cutting through the Earth's surface, shortest distance between 2 points, now we're starting to take into account the curvature of the Earth. And again, depending on which Earth you choose, those measurements may or may not be slightly different, right? So if we think about planar measurements versus geodesic measurements, you can think about planar measurements being okay for really short distances. But if we really want to get a true measurement on Earth, we need to measure using geodesic measurements, right? Because again, it takes into account how the Earth is actually curved and that it's not a 2D flat object. So now I want to talk to you about a clinometer. So a clinometer is an instrument that's used to measure, specifically in forestry, right? So forestry uses clinometers to measure tree height. And so the way that they do this is they'll measure one chain away from a tree, which is 66 foot. So you measure one chain away from the tree, and you have a tape measure that you pull at a horizontal measurement, and we're going to talk about that in a minute. You have a tape measure that you pull 66 foot away, and you want it to be at either eye height or between eye height and breast height. And from that measurement point, you're going to use this clinometer to measure up the tree, and you can actually determine tree height using this clinometer. So that's its most common use. So this will make more sense when you actually get to hold the clinometer in your hand on Friday. But for the clinometer when you're reading it, there's two scales in the clinometer itself. On the right side is that topo scale, which we use to measure tree heights. And then on the left is this percent slope that you can see. And you can use that to measure percent slope, right? So we can measure the slope of land using this clinometer. And that percent slope can be converted to angle, and we can start to make a lot of different calculations from there. So this is a good figure. Let me move myself so you can see of what you can actually see in the clinometer when you get to hold it on Friday. So again, you can see here that there's pluses and minuses on either side. And you can see foot scale and degree scale. When you play with this, it'll make a lot more sense again. There'll be a crosshair that you're trying to align with the top of whatever object you're looking at, whether it be the tree or whether it be the slope of the land. And then there's an additional degree scale on the actual side. So this degree scale on the side here isn't something you're going to be looking at. you'll be looking through this little black ring at the bottom. So that's where you'll actually be looking. And in that black ring, you'll see a rolling dial that looks like this. And that dial changes as you move up and down to give you that either tree height or percent slope. So we have this video using the clinometer that we're going to watch.
If you want to ace your paper, download Grammarly. Are you?
The other tool we can use to measure slope is a clinometer, which is a little more modern than the ABNY level. And instead of having a mirror with a level bar that's reflected it into the eye vision for you to line up with the level itself, this one has an internal dial. As I rotate the angle of the clinometer, it rotates this meter on the inside. So the trick with looking through the clinometer is I have to keep both eyes open, because with the ABNY level I could see through the tube to the other stake, but for this one I need to have one eye open to see the meter on the inside of the clinometer and the other eye open to make sure I'm lining it up correctly with the stake on the other side. So I'm going to go ahead and get over here and place the clinometer on top of the stake. Now, sometimes if your stakes are really close together, you need to make sure you angle the level meter line on the inside of the clinometer with just above the stake. These are pretty far apart, so I can aim pretty straight for the top of the stake and be good to go. Now, there's 2 meters inside this clinometer, and one side reads percent and one side reads degrees, just like a protractor that you might use in geometry class. Now, it's important to make sure you're reading the correct scale. This one happens to be a 1% slope. If I'm confused as to which scale is the correct one, I can always turn the clinometer up all the way towards the sky, and at the bottom of the percent slope, there will be a percentage sign. You'll also notice the percent scale goes up in number very rapidly, as opposed to the angle scale, which won't get to 100 degrees unless I was turning over backwards. It's really nice to have stakes to shoot your slope off of, but things happen. Sometimes they get knocked around by other wildlife or participants that are out on the site. If it's not the exact same height in both locations, you're going to need to adjust. And there's 2 ways to check that. One way is stand right up against the stake and mark a point on your body, walk down to the other side of the slope stakes, make sure the other stake is about the same height. If it's not the same height, you're going to need to slightly adjust which angle you're shooting at to make sure you're shooting at the correct elevation on the opposite stake. Another thing you can do to double check is shoot the slope both directions. I got 1% here, so if the stakes are at the same height, I should get 1% shooting back. It should just be positive in one direction and negative the other. If I got 1% here, but I got 5% when I shot from the other direction, I need to figure out what's going on. Are my stake heights slightly off, or am I, needing to work on my clinometer method a little bit better? Sometimes we don't have stakes laid out for the landscape that we're in to determine slope. In that situation, you need to find a partner on your team and a spot on their body that's the same height as your eye level. That way they can pace off in the appropriate direction for the landscape, and you can make sure you're shooting the slope on the right point. So with Keith here, I can tell my eyes are about the same level as his chin, that area on his body. So when he goes up a hill, I can make sure that I'm shooting to something that's the same elevation above the ground as my eye level.
A Dear LL Bean story, inspired by Thomas.
We don't need to watch LL Bean ads. So that's an example of how you can use the clinometer, and we're going to play around with them again on Friday, hopefully. So the big key takeaways here is when we're using the clinometer, we need to be shooting measurements from the same height, right? So the same height level. We need to keep both of our eyes open, one to look at the scale within the clinometer itself, and the other one to make sure that we're lining up properly. I put on here that, yes, this is hard. It is very difficult the first time you use it, especially if you've ever used a microscope. It's kind of similar to that, being able to keep both eyes open. So it is kind of difficult. And you're not going to be perfect the first time, right? So I prefer to use my dominant eye, put the clinometer over my dominant eye, and then use my non-dominant eye to make sure that everything is lined up. So my dominant eye would be my right eye. It's definitely my best eye. And so think about what your dominant eye is. And if you don't know, try to figure it out. And so you'll have that in the back of your mind when we start to use these on Friday. So when we're talking about that slope angle, we're talking about this angle here. So we're looking at the slope angle between point A and point B, and that's what we want to be able to determine, right? And so we can determine elevation if we know the slope angle, we know the horizontal distance, and we know the slope distance. And those are things that we can measure, especially over short distances. So here are two examples of measuring that slope angle. So we want to get this slope angle that I showed you in the previous slide, right? And so in order to do that, we need to put two stakes in the ground that are at the same height, and we can measure using the clinometer that slope angle, right? And so this works because as long as those two sites or those two stakes that we put in the ground are at the same height above the ground in their location, right? So if he put his in at 2 foot above the ground and she put hers in at 2 foot above the ground, as long as they're at the same height above the ground at that particular location, then this triangle will actually move up, and we can then take those measurements and determine the elevation change in that area. So how do we measure percent slope? So first, you can find a partner with similar height to you, like the video did, and you can find your ocular height on their body and use their person to determine slope change over a given distance, right? Or we can use stake methods. So we're going to use partner height differences when we practice this on Friday. So you'll just find a partner, any partner will do. You just want to find somebody and then measure your eye height on their body and then use their body as the measuring stick, right? So you'll look through the clinometers that I'll provide to you at your partner and read the number that's on the left side of them. And you're going to aim for their eyes, especially if the partner is your similar height, right? So if you're same height, you're going to aim for the eyes. If you're different heights, you're going to aim for that other body feature. Like in the video, she aimed for his chin area because that was where her height was, right? So when we're working on this, you need to be aware of the plus and minus on the clinometer. So there are pluses and minuses, right? So I want you to think about, when would you have a positive slope? So when would your slope be positive? So if you think about a positive slope, you should be lower where you're sitting and using the clinometer, and you should be measuring up, right? So then we have a positive slope. So if you then stayed in those positions and you threw the clinometer to your partner, then your partner is going to be measuring a negative slope down back towards you, right? So be aware of that. So if your measurements are starting to look wrong, then maybe we need to readjust partners and make sure that our ocular heights are correct, right? So if you are the same height and you're looking directly into each other's eyes, the clinometer should read 0, because if you're at the same height, there should be no slope, right? It shouldn't be up a slope. It shouldn't be down a slope. If you're truly are the same height, you should have a 0 slope. So we also need to work on measuring our slope distance. So our slope distance, this is the easiest one, right? So if you see here, I have circled in pink the slope distance. So the way that we measure this is by taking our tape measures, pulling the tape the length of the distance that we want to measure. So whatever distance that may be. When we're doing this, we need to be aware of anything that might be out there that make us trip, right? So be aware of obstacles such as down wood and things like that. And this is especially true if you do this for like surveying, or if you do this like in an area like in my background here, where the grass is literally chest high and you can't really see anything. So you have to be careful when you're moving around. This not so much on campus since we keep it manicured, but still important, right? So you're going to pull the tape along the ground, so right along the ground itself. Make sure that the tape measure doesn't twist or bend, because any twisting or bending or any looseness in the tape measure will change the measurement, right? So let's make sure it's a tight tape measure, make sure it's a straight tape measure that doesn't have any twist or bends in it, and then we can take a reading from there. So then to measure horizontal distance, so you can see that here in pink, you need to stop and think. So we know that we need horizontal distance. So that means that you and whoever your partner is must take a reading with that tape measure held really tightly and as level as possible, right? So with the slope distance, we're just following the slope of the land. So that's pretty easy. I apologize. These dogs are crazy. So that means that the tape measure, when we're doing the slope distance, we're just taking the tape measure over the slope of the land. But with the horizontal distance, we need a flat line distance. Again, that like planar flat line distance over that same area. So you can see that here where somebody is standing upslope and then somebody is standing downslope, and you need to hold that tape measure taut, right? So whoever's the tallest person in the group should be downslope so they can hold that tape measure up in the air, right? And so this may mean that you have to measure one line in multiple smaller segments, especially if your slope is really sloped, right? There's nobody that's going to be like 10 foot tall that can hold this up 10 foot, right? Like we just can't do that. So we might have to break up our slope into different segments. So I put here measure with your heart, but honestly, like you might need to take lots of measurements, right? And it's fine to take lots of measurements, especially if you want to be as accurate as possible. So take as many as needed, but as few as possible. I know that's like that's not great, right? That's not great advice, but it's the true advice. So take as much as you need, but as few as possible just to get a good, clear understanding of that horizontal distance. So then last, I just want to do an introduction to pacing. I actually have a worksheet for us to work on Friday. And in that worksheet, we will work on pacing, right? So we're going to learn what our individual paces are. It's kind of difficult. So I'm not going to be like grading you on whether you got your pace perfect or not. I just want you to start to think about what your common stride is, right? So we'll measure out a given distance, for this example, 100 foot, right? So we're going to walk that 100 foot as naturally as possible, right? So we need to just walk our normal pace. Don't think I'm learning how to pace or I'm trying to count my pacing. No, just walk your normal stride, right? So you want to be consistent every single time you practice. I think that we're going to do three trials. I can't remember exactly right now. My brain is like in a fog. But we're going to do a couple different trials to get an average pace for ourselves, right? So you want to be consistent with how you start walking and how you count, right? So you want to start off with the same foot every time, and you want to count consistently, right? And so I have here every step, right? So it's not every single time your one foot hits the ground. It's every time your left or right foot hits the ground, right? So if you take a step with your right foot, then your left foot, then your right foot, right? So it's a whole pace. So one pace is how the distance it takes for your right foot to hit the ground twice, or your left foot, depending on which side of your body is most dominant, right? And again, that'll make more sense when you watch the video that I have posted for today, as well as when we do it on Friday. So you want to walk that line 3 to 4 times, or until you start to get a consistent number of your pace. And then we'll do this calculation here, 100. So that distance, 100 feet, divided by your step count, what you counted while you were walking that pace, equals the feet per pace that you travel on average, right? And so we're going to go over this again on Friday, and we'll do a worksheet and we'll work together to get our pacing. So you can't ask me questions because we're digital right now, but if you do have questions, feel free to shoot them to me. I did want to show you that we're on week 5. Congratulations, everyone. Week 5. I'm so proud of us. And I wanted to show you that we have an assignment for lab today. So I'm not going to be on campus. So I decided to use a Google Earth lab for us. I will have my phone available. So if you do have any questions, feel free to shoot me an email real quick, either on Canvas or just through my regular email. And I can try to troubleshoot with you that way. If it's a really big question on this lab, please let me know because we can hop on Zoom like this and I can try to work through that way. So today I have this lab 5, which is Google Earth and Google Earth for storytelling. So you'll just click on this Google Earth, create a story map. And I have this really important point here that when you start this project, make sure that you select create project in Google Drive. If you do not select create project in Google Drive, then a lot of the features that are in this tutorial will not work, right? So make sure that you, I'll show you. So you go to Google Earth and you'll open this. This is the actual tutorial here. So we'll open Google Earth for web. And then we're going to start a project and we'll go to new project and we're going to select this very first option, create project in Google Drive. Like that's what you have to select. If you do not select it, it will not work for you. All right. I have 2 questions here that I want you to answer. So how might these skills be useful in the future? And how do you, this is a personal question, right? How do you think Google Earth compares to ArcGIS? How do you feel about using one versus the other, right? So then finally, I also have, after you watch this video, under our module week 5, lectures and video. So I'm going to post this video here. This is where you'll be watching it when you watch it. I also want you to watch this video here up to the 3-minute and 43-minute 3-minute and 43-second mark. It's all about pacing, so it'll give you a little bit better idea about what we're going to do. And I put these formula here so that you can understand what the math that we're going to be doing on Friday. And then finally, I wanted you to watch this video from 1947, which is a very cool video. And it's about projection systems and again, how projection systems are distorted. And we're also going to spend time on Friday wrapping that up as well. So getting caught up on the things that we've missed while I'm sick. So please do let me know if you have any questions. I will try to be available to answer questions. Hopefully I won't be taking a nap to sleep off the sickness. But I will be around to help you. All right. So with that, I will stop recording and upload this. And hopefully you all have a good productive day. And I'm sorry that my dog keeps barking. I have my dog and my parents' dog, and so they're crazy. But anyways, so I will see you hopefully all on Friday. And again, let me know if you have any questions that come up. All right, bye.